Well, good morning, everybody. Today's class is all about logic and some very, very basic terminology. Nothing's really complicated at all. So I'm going to start with the first one. And again, I don't come back to these definitions over and over again. I try to use simple language that you're very familiar with. The first one, though, and the author uses this a lot, is a predicate. Now, the funny thing is, I'm not an English person. You know, I took high school English. I took enough English in college to get by. And you guys remember, in a sentence, all sentences, if it's a legitimate sentence, can be broken up into two things. Do you remember what they are? Anybody? Your most basic English concept.
Subjects and predicates.
Subjects and predicates, yeah. And then you had, your nouns and your verbs and your adjectives and all that kind of stuff. This is called a predicate, and it's actually very similar, but it's not the exact same. In our case, a predicate is a sentence, but it's a mathematical sentence that has a finite number of possibilities. So my predicate could be something like, my predicate might be the integers, where x squared is greater than x. That might be my predicate. That statement. I'm not even sure that this is a correct English statement. So I might say that. Now, the definition of a predicate generally is a finite set of integers. Okay, so I now need to define a finite set that would make this true. Obviously, there's an infinite number of values that would make this true, but I am only interested in a finite set of values that will make this true. So maybe I'm going to define that set to be as follows, 2, 3, 4, 5, 6. And this set would be called my domain. Okay, the same domain where I'm drawing from. But the difference is, I'm not thinking of this in terms of a function. It's not that type of problem. The set of values that I draw upon is always called the domain. Okay. Now, my domain could be the set of real numbers. My domain could be the set of positive integers. My domain could be, the set of positive perfect squares. You could make whatever you want. But if this is my domain, then all of these make this true. That's a fairly simple thing. So what we start with is what we call the truth set. Okay. And by the way, it is possible for me to give you things that aren't true, and we'll determine how we decide things are not true. So the truth set would be, we'd write it something like this: the set of x's in D such that, and we're using what's called set builder notation. Most of you hopefully are familiar with this. The vertical bar in this context means such that. So the set of these things such that P of x. Now, there seems to be something missing here on the right side. I just said P of x. I didn't actually give you words. The concept here is that P of x occurs, or P of x is actually true, that it happens. So we save some of the verbiage right now. So this is kind of the most generic way we make the mathematical statement. I want all of the values that are in the domain that satisfy this or make this statement true, that causes this occurrence to actually happen. Okay, so this is kind of the way we're going to describe things. So in this case here, this would be the truth set. Every single one of these makes this true. So what if I gave you a larger domain? Okay, let's just have fun with that. I'm going to give you a larger domain then. Let's say I added to my domain 1, 0. This is still my domain. Would this set be the entire set here? Anybody want to try that one? Because this is called the truth set. I just made my domain a little bit bigger. What would this set be? Anybody can jump in here. No one wants to try it? Which of these values make this satisfy this?
All the values.
All the values?
All the values, except 1 and 0.
So in other words, how about my original set in black? Do you agree that the original set in black would work?
Yes.
But not the orange.
Yeah, now I understand what's going on. Yep.
So I tried to make that kind of clear. So the idea is my domain could be as big as I want it to be. My domain could technically be the set of real numbers, okay? But which of these make it true? Clearly, those are the only ones I'm really interested in. I'm only interested in the ones that satisfy this. Oh, okay. So now I made my domain a little bit bigger, but the truth set would be this set right here. Because it's all of the X's and D's that make it true. So it's not necessarily the whole domain. So the truth set clearly would be a subset of the domain. So now we want to introduce the quantifiers in this context. And now remember the two symbols, and we're going to use these a lot today, the for all and there exist. We want to introduce these and how we use these in this concept, in this context. So whenever I'm talking about a truth set, I want to say things like, for all X in D, P of X. Now we are really brief with the wording. This right now is another way of saying the truth set. All of the X's in the domain such that this statement is true, or that mean that this is true. Now, if I tried to claim all of this as my truth set, all of you would say, well, 1 doesn't work, 0 doesn't work. So whenever you're given one of these, this is called the universal qualifier. So this would be basically a universal statement. Okay, that's all that means. A universal statement is just for all X in D, the following things can be true. Universal statements are the easiest kind to disprove if they are not true. Now, here's where we sometimes get in trouble. Let's just say hypothetically, I said, let me give you an incorrect mathematical statement. For all X in R, X squared is greater than X. Okay. Do you believe this statement is true or false?
I believe it's false.
But aren't there an infinite number of occurrences where this is true? I mean, I just think of a parabola. I think of a parabola. This is y equal x squared. That's y equal x. So from this point on, x squared is always bigger than x from this point on. You're right. So I just gave you a statement that is true an infinite number of times. But is it ever false? Is this ever false? Well, how about everything over here? Well, no, that's not going to work. How about everything in here? Oh, so do you agree that from 0 to 1, this will fail? Does everyone agree?
Yeah.
Now, it's true an infinite number of times. Does it have to be false an infinite number of times? Now, by the way, this is a very, very important logical concept that a lot of people don't understand. For this statement to be false, we agree it's false. For this statement to be false, does it have to be always false? In fact, exactly how many times does the statement need to be false in order for the statement to be false? Anyone want to guess?
One.
Only one time. If I make this absolute mathematical statement, it is either absolutely always true or it is not, and I only have to show it's false one time. A lot of people make the mistake of trying to show it's always false. That's like saying, again, my thing of water is either full or it is empty. No, it's either full or it's not full. It's either true or it's not true. Not true doesn't mean always false. It means you can find one occurrence. For example, you said, what about 1/2? I know that the square of 1/2 and 1/2, that is not a true mathematical statement. I'm going to put a slash to it. That is less than. This is less than. This is what is called a counterexample. And I want you to be very familiar with that term. We don't spend a lot of time in this class looking for counterexamples. We want to be aware of their existence, though. To disprove a universal statement, and a universal statement is anything of this form, for all. I'm saying it is always true. A universal statement only has to be disproved with one counterexample. Now, I might say, hey, let's try to prove something is always false. That's a lot harder, by the way. I only have to come up with one counterexample. And usually the counterexample should be very specific just to make it easy on yourself. Now, what if you can't find a counterexample? I mean, I think about in calculus, you're doing something in calculus, you're going, God, I wonder if this is true. I wonder if I have a true formula. And you start plugging in random values and go, wow, it seems to always work. And it probably is always true. It's probably the case. If you can't think of a counterexample, it's probably the case that it's true. Now, that's not a proof. That's like saying, because I couldn't do the problem, there must be no solution. I couldn't find your house on the map, therefore you must be homeless. No, that's not how it works. But if you're trying something mathematically, and that usually is an indication if you can't find a counterexample. So in that case, that's fairly simple. Now, what about the other guy, the existential qualifier? There exists an X in the domain such that P of X. Now, we actually throw in, this is a new symbol for some of you, the backwards, this is basically the backwards element symbol. This is the such that. I'm used to using that. If you're not used to using that symbol, just write the word such that. When we did the set builder notation, that means such that. Okay, so that we have more than one way of saying it. We don't use this when we did the for all. We use this for the there exists because it makes the English make more sense. Okay, there is an X in the domain that makes this true. Now, remember, the D wasn't the truth set. The truth set were the X's in the domain that made it true. Okay, so I'm saying that this X must come from the truth set. This X must come from this set here. Okay, because I can have values. I can have values that don't make it true. So in the previous example, the X squared greater than X, my truth set would only be the X's that were greater than 1. Or on the other side, the negatives. It would be the X's excluded from the part that made it not true. So this is called an existential qualifier. So this is an existential statement, okay? And it's not very complicated. Now, to disprove an existential statement, and we're going to talk about that today, to disprove an existential statement is a little bit harder, okay? To disprove a universal statement, I need to come up with one counterexample. To disprove this is actually a bit hard because I have to show it's always false, and that's a little bit more work. I want to do a couple of examples now of this because we want to work on a little bit of translating. All right. So what I want to do is, first of all, I want to go through the English. One of the things we want to get really good at this course is to take a statement in English and translate it purely to symbolic notation. But then obviously we want to take something purely in symbolic notation and translate it to English. We want to be able to go back and forth easily. That way we can write all of the conditionals, contrapositives, and things like that. We can write the negations both in English and symbolically. So let me take a couple simple statements here, and let's see if we can translate them. Excuse me. Okay, here's my first statement. It's, by the way, when I make the statement does not necessarily have to be true. Okay, this statement could actually be false, but I'm making a statement. I want to be able to translate it, because if I can translate it, then it makes it easier to determine its truth or its falsehood. I gave you a universal statement. Ooh. Now, go ahead and unmute yourself for a moment if you think you can translate this. Now, I can't see who's talking, so there's no penalty for being wrong. But I want to translate this in English. And, don't be super, super formal when you're translating to English. Translate it as if you're talking to somebody.
Can I try?
Yeah, go ahead and give it a shot.
For all x, for all positive integers, for
Good.
all x belonging to positive integers, such that x is greater or equals to 1 divided by x.
Okay, that was very mathy, though.
Yeah.
What's another name for this guy here? Rather than say
Repro, something.
reciprocal.
Yes.
Reciprocal. Now, you said for all x in the set of positive integers. If I'm translating this into English, I'm never actually going to use the term x. I'm going to say for all positive
Numbers.
integers. Oh, this for every x in the set of positive integers. I'm actually saying for every positive integer. So in other words, I drop the x when I'm translating. This says every positive integer. Oh, okay. Every positive integer is at least as big as its reciprocal. Because if I'm speaking to you in English, I want to use less math symbolic things because then you have to keep translating. This says every positive integer is at least as big as its reciprocal. Now, is that a true statement? What's the only number that you might even question here? You know, 5 is bigger than 1/5. 1,000 is bigger than 1 over 1,000. The only one that might be an issue is 1, but 1 is equal to 1 over 1. I put in or equal. So actually, this is a true mathematical statement. Okay, that's nice that it's true. If I had made that a strict inequality, would it be true?
No.
No.
Because, keep going. If I take away this, it's false because there's an infinite number of positive integers. And you're saying you believe this statement is false because that's not true. That would be the one and only counterexample, but that's all you needed is 1. Oh, okay, every integer bigger than 1 is bigger than its reciprocal, but 1 is equal to its reciprocal, and I said or equal. So the translation, okay, the translation. So now let's go in reverse. The square root of every positive real number is real. First of all, do you believe that's a true statement? The square root of every positive real number is real. True or false? Just saying.
True.
Yeah, if I said the square root of every real number is real, that would be false because if I took out the word positive, tell me why that would be a false statement, by the way.
Square root of negative numbers are imaginary.
Yeah, and that's kind of important. So this is a true statement. Now, what I'd like you to try, and everyone try this on your own, just for 30 seconds. I would like you to translate this symbolically so that it looks like the last one. I've given you an absolute mathematical statement. It is a true statement. By the way, I could make it up and be false. The translation has nothing to do with whether something is true or false. And that sometimes gets us. So never worry about the truth or the falsehood of the statement itself that you're working on. This is just the vehicle to practice on. Okay. I could say something silly like the square root of every positive real number is 5. Well, that's not true, but you can still translate it. All right. So the square root of every positive real number is a real number. We want to keep this really simple. Anybody want to start this for me?
You can use a for all quantifier and then make x an element of r plus.
Beautiful. Okay, let's just stop there for a moment. I love this. Right now, this says every positive real number. There's no way you can look at this anywhere else. Every positive real number. Don't say every x in the positive real numbers. We put the x in there so we could then describe what's happening to x. This says every positive real number. Okay. For all positive real numbers, what?
And then I guess you could do square root of x is an element of r.
That's it. Let's walk away. Let's admire our beautiful work. That's perfect. I couldn't have said that any better. By the way, technically it would be r plus, but that's not what that says, right? That just says it's real. Is it positive real? Yes, but we're translating these words. This is a perfect translation. And here's what I love. It's symbolic, it's clear, it's clean. There's not a single word Yet it's absolutely a perfect translation. This is the kind of stuff that a discrete math student must be able to do at some point. Go from words to statement in symbolic notation and symbolic notation back to words. Okay, so here's where I have some fun with this. I will give you this statement and I will say, translate this into English. And a lot of us have a difficult time. So here's what I've seen people do. I'll ask this on an exam and I'll have people go, well, I'm going to translate it in English, and I'm saying without using any symbols. All right, for all X an element of, I think we've completely missed the point. I am actually just reading this off in symbolic. I've actually had people do this. This is funny. That's, I'm spelling the word X. No, this is not even like it. When we translate something, we want to use words. So in other words, a translation should never have a for all or a there exists, because all I'm doing is replacing the symbol with the exact words. X is an element of the positive real numbers. Those are not the words I'm going to use. I'm just going to say for every positive real number or all positive real numbers. Again, the words should not sound like the symbols verbatim. So the square root of every positive real number is real. We've written it like this. So this is one of these that, then again, that should make sense. All right, now let's try another one. There is a positive integer that is smaller. Oops. There is a positive integer that is smaller than its cube. There is a positive integer that is smaller than its cube. I would like to write this in symbolic notation. Am I saying all positive integers are smaller than their cubes? Am I making an absolute universal statement here? No, I'm not saying all. Are there a lot of positive integers that are small? No, again, it doesn't matter if something's true or not. That's not the point. I want to translate. I'm saying there's a positive integer. How many of them am I saying there are? Ooh.
One.
At least
Well,
one.
at least one. At least one, right?
At
least one.
Good. I'm not saying there's exactly one. I am saying there's at least one. Might there be 7? Might there be 12,300? Might there be 1,000,000? Sure. Might there be infinitely many? Sure. Well, all I'm guaranteeing here is there's at least one. How do I know that? Because I said there is. I didn't say everyone. I just said there is one. There is one. Now, might there be more? Of course there might be more. I'm only guaranteeing one. And that's really important when you're looking at the words here, because that may not be obvious at first. So how can we translate this one? Okay, so what am I going to start this one with?
The exists sign, the E,
Good. There exists.
and X
And at
in Z plus. So
Good. I love this symbol because it is so easy to interpret. Tell me what other symbol, and by the way, if you're in Calc 2, you wouldn't use Z plus. There's another symbol that's always used, and because I use it. Does anybody know what the symbol we would use in a lower class than this? There was another number group that is the same thing, and we use that symbol. If you could look at any Calc 2 book, sequences and series, it's always the same. I'm just curious.
natural numbers.
Capital N. Natural numbers. Capital N is the natural numbers, and in calculus books, you'd always say, for N in the natural numbers. You would always use natural numbers because that's where the indices come from in the summations and the sequences and stuff. But they also come from positive integers. In this class, we usually do this because we concentrate more on the integers than any other number group. So positive integers, the entire integers, it's easier. So this says there is a positive integer. Now, with this always comes, I'm going to help you out, always the such that. With a there exists, there must be a such that, otherwise the English doesn't follow. With a for all, there isn't a such that. There's a positive integer such that, keep going now.
X is less than X cubed.
Beautiful. You guys have, we're getting a PhD in symbolic notation here. That's excellent. That's perfect. That's exactly what it's supposed to be. And you're saying, God, that's just not that hard. That's a fairly simple thing. So a lot of times we can make an English statement and then we have all sorts of ways of translating it. So let me make a statement. I'm going to make a mathematical statement, and I would like you to translate it for me. Okay. Excuse me. Let's say, let's say, oh, actually, I'm gonna make this simpler. Make it simpler. I'll say, okay. I would like you to now translate this into English, but what I want you to do is translate this more than one way. Ooh. Boy, that's a tricky one. I'm going to translate this more than one way. By the way, if this was a question, this is the only question on the exam. Translate this into English. Do you think that I'm going to get exactly the same translation for every single person? Well, obviously the answer is no. But is it possible I get different translations and they're all correct? Actually, yeah. Because you could all be saying the same thing. You just use a different choice of words, maybe the order of the words. So let's see if we can make sense of this. In English, anyone want to try this one?
There's
In,
an x that makes e to the x equal 10.
I'm sorry, say it again. There was too much other.
All right. There's an x that makes e to the x equal 10.
Okay. All right. Let's stop there. There is an x that makes e to the x equal 10. All right. Does anybody have another one?
There's a real number that exists where e to that number equals 10.
Okay. Okay. I want to avoid using there exists though. I like what you said the first time, that there is a real number. Okay. Anybody want to try it? By the way, both of these are good.
There is a real number such that the natural exponential function equals 10.
Okay. Okay. You guys are getting very mathy. Now you got to explain this to your 10-year-old sibling. Here's one I like. E to the x equals 10 at least once. You like that one? By the way, that'd be the same as saying for at least one real number. By the way, everybody said something correct so far. Oh, so that means that if what I'm saying is correct, I could use a different choice of words because the order of the words I use matters. But how about if I said this? E to the x is always 10. What do you think?
Negative.
That's incorrect.
No, because that's not what this is saying. What is this saying to you? What is that telling you in simple English? By the way, if this statement is actually true, which
It happens at least one time.
it happens at least one time.
Minimum of one.
In this case, in this particular, for this exact problem, does it happen at least one time?
Yes,
At least one time?
but it happens once, but
It happens exactly one time in this case. Do you agree? Oh, e to the x is only equal to 10 once, and someone used logarithm when x is equal to the natural log of 10. But that's the fact that it's only true once isn't important. The fact that it is true ever is the thing. So if I said translate this, and the first question on this quiz tape, by the way, I've given you this statement, and then I've given you 2,647 different translations of it. I cut it off at like 10 though. And then I'm saying, which of these are saying the exact same thing? And now you got to go, oh my goodness, I'm rearranging the words, but this one says the same thing. No, this one's not true. This one, no, this is not true. Oh, but wait, no, this is saying the same thing. I've rearranged things, and you have to look at it and say, which ones are saying the exact same thing? That's a little bit tricky. It's not meant to stump. It's what the exercise we just did. I just got 4 or 5 beautiful translations from you that you all said something different, which means that there must be multiple correct ways of interpreting this. In the end, we agree that x equal log 10 is the only solution to this, but that is a real number and there is a solution. Okay. Now, simple translations. All right. Let's say, I was doing a recent poll and I found that every Math 245 student is a hockey fan. I didn't ask very many, but it didn't matter. All right. I would like to now translate this using quantifiers and variables and things like that. Now, again, this is an exercise. You go, oh, and variables. Yeah, a lot of us get caught up thinking variables can only represent numerical quantities. No, if you've ever had statistics, the term random variable, that I love it. It's neither random nor truly a variable. A random variable is the set of all possible outcomes an experiment can have. But my experiment can have nominal data, in other words, names. So in other words, I might be doing an opinion poll on, let's say there's an election coming out and you've got 5 different candidates, and I'm doing an opinion poll as to which candidate you're going to vote for. There's no number. I'm voting for the number 3. I'm voting for the letter A. No, you voted for Smith. Someone else voted for Jones. It's called nominal data. There's no numbers. Now, I might say here's the number of people who want to vote for that person, but the variables would be the different names in this case. Oh, a variable doesn't necessarily have to represent a quantity. So in statistics, we talk about the 2 types of variables. There are qualifiers and there are quantifiers. Quantifiers are numerical values. Qualifiers are descriptive values. Okay, I might be talking about color. I have a whole bunch of colors. I might be talking about music choices. These are not quantifiers, these are qualifiers. Oh, so variables can be either one. So I just want to make that clear. So you might be the variable. So in this case, obviously the variables are the students in the class. So X might represent any individual in the class, but only individuals in the class. So that's why I want you to don't think of variables numerically and necessarily. Variables are just from the set of my domain. My domain in this case would be the class roster. So does anybody want to try this? I've left you very vague instructions. I want you to translate this into a mathematical statement. Again, quantifiers, variables.
X equals Math 245 students.
Well, you can make it easier. For all X in the Math 245 class. You just say it like that if you want. Or let's say for all 245 students X. Now I've just now said X represents a 245 student. You could start off by saying let X be the set of, or let X be an element of the set of 245 students. That would be correct. It'd be overkill. For all 245 students X, yeah, you're going to use English, but we want quantifiers. How about X is a hockey fan? Now you could get really formal. You could get really formal and say, let's describe M is the set of 245 students, M for math. H is the set of hockey fans. And now you can say for all X in M, X is in H. Would this be a correct mathematical statement?
Yes.
This is killer.
Yes.
But in words, this would be good enough. In the super strict formal, this would be correct too. Okay. So I'm just taking a simple English statement and I'm translating it. Okay. Now, how about I just had my world torn apart here. I realized that when I was asking my questions, I somehow messed up the yeses and the nos, when I interviewed all my 245 students, and I realized that it was just the opposite was true, that none of them were hockey fans. So how do I do that one?
You just put a negation in front of the X as an element of H.
So that's how would I do that? Certainly it's X. Well, it's actually easier if I start with this one, believe it or not. Now I'm saying no math students. So can I start with for every student in the math class?
Yes.
Now what?
Now you put a negation in front of the.
That may be correct, but that's how do I say it is not the case? By the way, you're right. It is not the case that X is in H. Could I just say X is? Would that work?
Oh, not an element in H. Yes.
But it is not the case that X is an element of H is correct. But what does that actually mean? Oh, that means that X isn't in the set. Okay. So now let's go back to here. For all 245 students, X is, oh God, it just hurts to say.
Not a hockey fan.
Not a hockey fan. We know this isn't true, but that's not the point. Does everybody see how easy that was to make that? So is the no, in a sense, universal? Ooh, this is a tricky one. Everybody does the following thing. Nobody does the following thing. Is nobody a version of for all? This is kind of the segue into the next thing we're doing today. Is nobody a version of for all?
Yes.
Yeah. For all things, yes. For all things, not yes, would be, kind of like saying no for everybody. Yeah. So that's none is kind of a tricky one. None is kind of a tricky one because we don't always think of it that way. If I said everybody in the class is a hockey fan, okay, for all students, they're hockey fans. Nobody in the class is a hockey fan. How do you do that? Yeah, for every student in the class, they're not a hockey fan. So you can do that. And later on, when we get to the numerical parts of this, it turns out to make things really nice from a mathematical point of view. The calculation for none is much easier than the calculation for some, right? The calculation for some is more complicated than it is for none. I'm going to flip a coin 1,000 times. I want the probability that I have no tails. It's easy. It takes 2 seconds. Find the probability of any other outcome is kind of gnarly. So we like that one. So now we want to go to negations, because negations are one of the harder things. This is true for every 245 class. Correctly stating negations is probably the toughest thing for people to master as a group. I'm not sure why. It just, from a symbolic standpoint and just a conceptual standpoint, negations seem to throw people. And so I want to start with the simplest versions, and that's the negations of universal and existential statements. So for all X in D, P of X. This is our universal statement. And by the way, let's make the assumption that this is a true statement. In other words, remember how I said it before, that it's only the ones that make it true that I'm interested in. So for all the possible things here. So now maybe I'm just talking about, and now I realize a lot of the class is hockey fans, but not everybody in the class is a hockey fan. So I only want the hockey fans in class. So D is the domain. That would be maybe our roster. So I want all the students in the class, and then P of X is you're a hockey fan. That I'm not saying everybody in the class is a hockey fan now. I'm just saying I'm looking for everybody in the class that is a hockey fan, and that's the group I'm talking about. Keep it really, really simple. For all X in the domain, P of X, that's a true statement. Now I want the negation of this. So you don't have to think hockey fan example, but how do I negate this statement? The negation of this. Ooh, for all X in the domain, P of X. Now I want to negate that. For all X in the set of real numbers, You know, x squared is greater than x, or something like that. By the way, it doesn't matter whether that statement is true or not now, just in just a general sense. So if I said, for all students in this class, you're over 6 feet tall. It doesn't matter if that's true or not. I'm just making a statement. Remember, a mathematical statement of any form is either true or it's false. It can't be both. It can't be ambiguous. So if I just said, everybody in our class is over 6 feet tall, that might be a true statement. But some of you go, wait a minute, I'm not over 6 feet tall. Okay, so now it's a false statement. I don't care. I'd like to say the negation of that. So let's start with something really simple. Everybody in our class is over 6 feet tall. What would a negation of that be?
Not
Everybody in
all,
the class is under 6 feet tall?
not
At
all,
least
maybe.
one person
At
is
least
not.
one.
Good, you guys have figured it out. What is the negation of my jug is full? My jug is not full. Remember, it's not the antonym, it's not the extreme opposite. So the negation of everybody in our class is over 6 feet tall is there's somebody that isn't 6 feet tall. By the way, what if everybody was shorter than 6 feet? That's okay, but that's not what we're saying. So the negation of this would be there exists an X in the domain such that always is such that not P of X. And I'm going to be really generic because it depends what the statement P of X is. P of X is maybe they were a hockey fan, so now they're not a hockey fan. P of X might be you got a positive number. So not P of X means you got a non-negative number. Okay.
Professor,
Yes.
I'm starting to get a little confused with the symbols, just due to the fact, why do you have comma in the first and now it's an arrow in the second? Before the PX.
Not an arrow.
All
It's
X in the domain, P of X is a true, P of X happens.
Oh, I see. Sorry. Okay. Someone else also said it. I thought it was an arrow. It's something else. My bad. Thank you.
He's talking about the such that. He's talking about the such that
Yeah.
symbol.
Such that.
Yeah, the such that, because you have to have that with at least if when there's only one exister. Yeah,
The
my
reason
bad.
you throw the such that with this is if I just said for all X and D not P of X. No, I'm sorry. There exists an X and D not P of X. There exists an X and D.
Yeah,
That from a grammatical standpoint, you're going, there's something missing. Yeah, it's there is this such that the following thing is going to happen. I don't need a such that for all X and D this happens. You wouldn't put such that in there because that just doesn't sound right. In other words, think of it from an English standpoint. You always have a such that here because you want the sentence to make sense. So for everything this is true, there's at least one thing where it's not true. Everybody in the class is a hockey fan. There's at least one person in the class that's not a hockey fan. Does that make hopefully that makes perfect sense to you guys. Now I'm giving you the generic so that you can then attack things. So let's do a simple example of something. Okay. For all X in the set of positive integers, X is, let's say, for all X in the positive integers, X squared is 1,000. Okay. You know that's absurd. It doesn't matter. You know that there's no truth to that statement. It doesn't matter. I'm just writing a mathematical statement here. I'm writing something that makes it really easy to negate. I could have said anything here. Remember, a mathematical statement is true or it's false. That's not our intention here. Our intention is to write a negation. You know, if I said come up with a counterexample, I think we could be coming up with counterexamples forever and ever and ever. So how do I negate this? I'm saying every positive integer that exists, its square is 1,000. How do I negate that? There exists an X in the positive integers such that what?
X squared is not equal to 1,000.
Yeah, that's it. By the way, you don't have to say X squared equals something else. You just have to negate that. Oh, what is the negation of I am standing here? What is the negation?
I'm not standing here.
There. That I'm not standing. Yeah, be careful because I'll say, what's the opposite of me standing here? You're standing there. Well, what about there or there? No. So people get, yeah, the negation. If you start with the not, now remember, most of the time, just simply throwing the word not makes it really easy. I said the exception, and I want to make sure you guys are paying attention because this is black and white right here. When do you not use not when you're negating? When your choices are what was the word I used? Do you remember?
Binary.
Binary. You don't ever say the light is not on. The statement is not false. No, when it's binary, you state what the not is. So not on is off. Not false is true. You don't state not when there's only two possibilities. Oh, so if I said my cup is full or my cup is not full, that is correct because there's an infinite number of states of not being full. But if I said it's 1 or it's 0, it's not 1. Haha, I'm giving you a hint. No, it's 0. And sometimes we get kind of goofy. There's an infinite number of values other than 1,000. So it's not the 1,000. There's an infinite number of choices of numbers here. I can't start choosing them because this isn't a binary. Oh, so this is why this is literally throwing the word not in front of here. It's either 1,000 or it's not. It's not either 1,000 or some other number because there's an infinite number of choices there. On the last quiz, some folks had trouble with, we had a problem with an inequality. Inequalities are binary, you know? So in other words, what is the negation of greater than 0? What's the negation of that? Anybody?
Less than
Or equal to.
Less than or equal to 0. It isn't the word not greater than 0. That's it. That's like saying not off. No, greater than 0, less than or equal to 0. Those are the only two possibilities with that particular inequality. You don't use not on an inequality because there is only one other option. In a sense, it's binary. I'm 1,000 or I'm not. I'm not even talking about another number here. So this is perfect. So first of all, if you don't get anything else out of today's lecture, the negation of a for all is there exists, period. So I like to say it from an English standpoint. The negation of for all yes is there's at least one no. That's an easy way of thinking about it. Everybody said yes. What's the negation of that? Not everybody said yes, so at least one person said no. That's an easy way of thinking about this. Now, what about the existential? There exists X in the domain such that P of X. I'm saying there is at least one occurrence where my predicate happened. There's at least, and always substitute numbers and mathematical statements into this if it makes it easier for you to digest. There is at least one real number that equals its own square. Maybe it can be something like that. Okay. There exists an X and D such as this. It's true at least one time. What's the negation of it's true at least one time?
There's none.
Yeah, it's never true.
Oh, it's
That's a tricky one. That's not exactly obvious. The negation of there's at least one occurrence of something is no, there are no occurrences of that thing. So in other words, the negation in words of it's true at least once is that it is never true. And by the way, from a calculation standpoint, this is one of the more powerful rules that makes it really, really easy. I'm going to give you a hint because I used to teach stats. Some of you have done this. You know, I want to play a slot machine over and over and over again, you know, and I know what the probability of winning. So if I said, gosh, I'm going to play, you know, I have all day, I'm going to play 5,000 times. What's the probability I win at least one time? Well, that would be a really gnarly calculation because that means I have to calculate winning once or twice or 3 times or 4 times, all the way up to 5,000. That's a lot of calculations. Or I could do the negation of winning at least once, which would be winning how many times? And that calculation takes 5 seconds. And then all you do is you subtract that from 1 and now you have your answer. It's called the law of at least once. There's actually a mathematical formula for calculating at least once, and it's by using the negation, because the negation of at least once is none. And from a mathematical calculation standpoint, that's one of the most powerful rules we ever learned because it makes a complicated process unbelievably simple. If you've had stats, I would hope that you've seen that one before. So the negation of this. how do I say this symbolically? How do you say none?
In all of,
So we have to start with for all. Yeah, remember we said never, we can say for all. So for all x in D,
negation P of X.
beautiful, perfect. And by the way, this is ambiguous sounding. Well, I have to give you a statement before you can tell me what this is, because P of X may not be binary. So I may actually just simply write the words. But what if I was using words like, for all students in the class, they're gonna live. I guess the negation would be they're not going to live, which would be the equivalent of saying they're going to die. I know it sounds terrible, but think of something that actually only has two possibilities. For all students in the class, they tell the truth. So if it really is truly binary, that makes it easy. Most of the time it won't be. So let's try this. Okay. There exists an X in the set of real numbers such that X is greater than or equal to its own square root. Again, it is not important whether the statement is actually true. Everybody got that? It's not important. Is this statement true, by the way? I mean, can you think of values
Yes.
of X that are bigger than, yeah, pretty much every real number greater than 1 or greater than or equal to 1. So it's not a question of whether it's true or not. I just gave you a statement. Sometimes it helps to think whether it's true, but when I'm trying to write negations or things, no, it doesn't matter if it's true. It's irrelevant. So I want to write the negation of this. There's an X in the real number such that the following thing happens. That's why I need the such that to make the sentence complete. So the negation of a there exists is a for all, it doesn't exist. So for all X in R, now this is simpler. How do I say it is not the case? And by the way, you would never leave something in this form. It's not a complete answer. This is what I'm going to write next. I'm going to say, what is the negation of this statement? Anybody?
It's just
X less
comma.
than.
Yeah. That the negation of this statement is that statement because it's an inequality. If I had put an equal sign here, then you would put a not equal sign here. You wouldn't leave it in this form because again, it's a little bit ambiguous. You're saying it's not whatever that says, but what is not whatever that says? I can complete that sentence. So the negation of an existential qualifier is a universal qualifier. The negation of a universal qualifier involves an existential qualifier, but with the opposite result. So
Professor.
again, question.
When it also comes to symbols and just understanding things properly, would you say then these two rows, the way you could also connect them is with the 3 equal lines?
I'm sorry. I'm sorry. With which?
So for the these last 2 rows that we just worked on of the X is greater than square root of X, and then would you be able to put the 3 equal lines and then it means it's the same?
Oh no, it's the careful. The negation of this. I think this is what you're asking.
That is what I'm. Yep. So
Okay,
we can
yeah,
say
I
that.
wouldn't use it on this statement. I'd say yes. This would be a correct
Okay.
interpretation. Yeah.
Cool.
Because the negation of a statement, right now, you know the first statement. Now I'm putting the squiggle in front of it. I'm saying the negation of the statement. I'm saying I want you to negate the statement, but that isn't obvious what the negation of the statement is. I actually have, it's like a calculation. I have to go through and calculate what the negation of the statement is. So now we're saying this is what the negation of the statement is. So here was a mathematical statement. The negation of this mathematical statement is equivalent to this statement.
That's what I asked. Perfect. Thank you.
Good. Yeah, but I had to throw that in there first. By the way, I love the thinking because that's correct. I would never ask you to break it down into that specific. I'd just say, what is the negation? And you go, okay, the negation means I'm putting a squiggle in front of the whole thing. How do I say it? And I mentioned before, one of what we consider in this class, one of the single most important skills is to negate anything. Doesn't matter what we're saying mathematically, how do I correctly state a negation? That is not obvious, but after a short period of time, you actually get pretty good at it. Now, we're gonna do an exercise because we haven't talked about this much today. But one of the really important overall logical concepts going back to the conditional statements. The ideas of converse and contrapositive and inverse and things like that. So I'm going to start with a simple mathematical statement, and then I'm going to give you an exercise. All right. I like using something that is easy to conceptualize. All squares are rectangles. Now, what I'd like to do and we're going to take a few minutes for this one. I want you to write this as a conditional statement. That means I want you to take this statement that I just made, and you need to write it in if-then form. Okay. And by the way, I'm giving you a true statement. So it's not a question of is it true or not. I want you to write it in if-then form. So anytime you make an absolute statement, I'm going to the store today. How do I make that into an if-then? If I leave the house, it will be to go to the store. I guess you could say it like that. But you want to make this into an if-then statement. So then you can write the converse, the contrapositive, the inverse, and the negation, which will probably be the hardest of the bunch. So I'm just going to give you a couple minutes. I want you to all try this. I'm going to pause just for a moment because I don't want to record, the thing. I'm going to record again because I want to get the answers. If a shape is a square, keep going.
Then it is also a rectangle.
Or just then it is a rectangle. How's that?
Yeah.
Now, if you believe the first statement was true, then the conditional pretty much has to be true. If a shape is a square, then it is a rectangle. Do we all agree that that actually is a true statement? And it does reflect that. Hopefully you say yes. Okay, now let's go from here. So if you want, the P would be my shape as a square, and the Q would be my shape as the rectangle. So I just wrote P implies Q. So what is a converse? From this notation, what is the converse?
Q implies P.
Q implies P. And again, I said, don't worry about the truth of the statement. I just want to make the statement. So what would the converse be? And all of them should start like this, more or less. If a shape, help me out here,
Is a rectangle,
is a rectangle,
then it is a square.
then it is a square. And by the way, I have used this example in class. Then it is a square. It is a square. This is getting a little bit tight. Now, just staring at that the surface, the conditional is true, but you're going, a converse, I don't think that's true. I can think of a rectangle that isn't a square. I don't think that's true. Illustrating that when a conditional statement is true, a converse is not necessarily true. In fact, you're going to find most of the time the converse is probably not true. Now, notation wise, what's the contrapositive? Think PQ.
Not Q implies not P.
Not Q implies not P. So let's state that one. If a shape is
Not a rectangle.
not a rectangle, then
It is not a square.
it is not a square. If square implies rectangle, and I have something that's not even a rectangle, how could it be a square? It's not a rectangle, it's a triangle. It's a circle. If it's not a rectangle, it can't be a square. Square implied rectangle. Rectangle was the bigger set. Here's an easy way to think about this. I like doing it this way. This is the set of rectangles. This is the set of squares. Do you agree that it lives completely inside the set of rectangles? Should. Because I can have rectangles that aren't squares, but I can't have squares that aren't rectangles. So if I have something that's not a rectangle, it's completely outside this set. It's definitely not going to be a square. So that is correct. Now, the inverse. This is probably the most obscure of the bunch. That's why when we're doing logical statements like we did last day, inverse errors are common because I can get them backwards easily enough. What's this guy?
Not P implies not Q.
Not P implies not Q. So if a shape is what? If a shape
Not
is
square. Not
not
square.
a square, then it is not a rectangle. Is that a true statement? I'm thinking of a shape that's not a square. There, that one's not a square, but it was still a rectangle. Oh, I can have shapes that are not squares and still be rectangles. So that's actually not a true statement, because the converse is also not a true statement necessarily. Ah, now the last one. Symbolically.
P
and
implies
nug.
Careful. There's no implication in the negation. That's where we get into trouble.
It's P and not Q.
P and a, beautiful. Now in English, there's a word that we often throw in here. This is one of my favorite things, because in English language, there's a word that we don't even realize sometimes. There's a word that negates. I was like saying things like, I love you, but you're like the greatest person I've ever known. You do all of these wonderful things. Everybody in the world loves you, but the moment I throw but, what happens to everything that I just said before it, by the way? Universally, what happens to everything I said before it? When you throw
Negated.
it negates everything you ever said. People don't realize the word but automatically negates everything you just said. That's why in a negation statement, we actually use the word but. I always like to say, I love you, but. So how do I say this?
Either shape is a square or
How about I just start with a shape? P was square a shape is a square,
but not a rectangle.
but it is not a rectangle. Exactly. Could I use the word and?
Yes.
Yes.
Yeah.
But it is not. I want you guys to make sure you understand that, because the formal logic says and. But in the English language, I have a shape, it's a square, but it isn't a rectangle. You wouldn't say I have a shape that is square and it's not a rectangle. That is absolutely a correct statement. But the but emphasizes the fact that something just failed, but it is not a rectangle and it was supposed to be a rectangle. So you could use the word and here, it would not change the meaning at all. In this context, but and are the same thing. Your previous quiz, hold on, you had a problem. So I can find the question. I think it was quiz 2. Don't know that I have it. It was the Isaiah likes math or hockey, but not broccoli. You remember that one? So when you wrote the connectives, it was and not broccoli. Because that's the right thing. So when you use the word but, the connection is and when you use the word and, you can use the word but if I'm using the word but because I gave a negation, so that from an English standpoint, this makes sense. Absolutely to put and. Now, there's nothing tricky about anything that I said. Translating into these means you understand the meaning of these. So just so you know, it's one of my favorite, maybe one of the more important questions that we deal with in all of discrete mathematics. It's on your next quiz. I start with the statement, Luke, I am your father, join the dark side. And I'm asking you the exact same thing. Conditional, contrapositive, negation, okay? So the start is, it must be put in an if-then format, and then I can go from there. Because everyday language, and this is part of the bigger picture, and now I'm speaking to the programmers among you. If I make a statement, a true statement, we know there's more than one way to interpret that statement correctly. And again, we know that this and this are exactly the same meaning, but one is stated with negatives, one is stated with nots. Okay, we know they're the same thing. So a lot of times it's convenient to do things other way. When writing a mathematical proof, I want to show that given this, I can conclude this, but sometimes it's very difficult to do the direct path. So instead, we might start with assuming the opposite of this, the negation of this, and show that it leads to the negation of this. Okay, that's called a proof by contrapositive. Okay, so sometimes that's a very powerful proof. In high school geometry, that was commonly a proof. You prove things by assuming the opposite of what you're trying to prove and show that it leads to the opposite of what you can assume at the beginning. Those are very powerful statements because we understand the logic behind them. Now, that's as far as I wanted to get today.